work at the end of this week. So you see, I don't know the program for now. I don't know the program, but I I hope I will speak with your lecturer and I will check. Uh, I will check the problems. You see, maybe for other seminars they have something which we do not have. So I will check that all the questions, as for the written work, will be in the scope of our seminars. You see, you understand me?
Yes, we got
Yes, we
it.
understand.
We understand.
First, because it is very important. If we go very fast, uh, it will be not very good for you, to my mind. If you want to go faster, no problems. I will include in our seminars several topics and so on, so on. But I want to explain you some things, and I want that you can understand these things. You see. So if you are not agree, we will change the method
I think it's good.
Yeah, I agree too. I think it's good.
because we can discuss something not very fast, easily, with some examples and so on. So you see, I repeat, uh, as for this written work, will I will say that now, for now, we are in differentiation and nothing else. You see, because it is possible also to find the limits with the help of the derivatives, L'Hopital rule, and so on. But for now, we are here. Okay?
Okay.
Yes, it's good.
Okay.
Okay, good. So let's start. So differentiation. The first slide is like this. So you see the definition of a function phi sub a of x. So I do not repeat, consider a function something like this, but the idea. I take my function f of x minus f of a. So this function have to be defined at this point. And f of x minus f of x is over x minus a. So you see, this function really, in fact, is not defined at this point a. Agree?
Yes, I agree.
Agree. So the second point of this definition, I say, if there is a limit of this function phi sub a as x goes to a, then 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 we can say that this this function, you see this one, uh, is a derivative of my function f of x at the point a. And you see, the formal definition is here at the bottom of this
I'm sorry,
definition.
could you explain it again, please?
Pardon?
Yes, hello. Could you explain what you said a while ago again, please?
So you see, I say, I return to the first slide. So I want to discuss with you the limit, this one. Can you see the limit?
Yes, I
The
can see.
limit, yes. So,
Yeah,
so this limit maybe exists, maybe not. Okay. So what I want to say that there is the derivative of my function. I do not want to read all the words in these slides, so you can read them. So if I have this limit like this, can you see?
Yes.
Yes, I can see.
Then you see, I say that there is a derivative of my function f of x at the point A, which is defined like the limit as x goes to A, f of x minus f of A over x minus A. So formally, very formally, you see, I say that my function has a derivative at some point A, and this derivative is defined by this rule, by this formula, by this limit. What you prefer, I don't know. Is it clear?
Okay, it's clear
Yes,
now.
it's clear for now.
So you see, for the moment, only for the moment, I do not speak about something like strong results, but only I want to give you a definition which is given in terms of a limit. And this limit, I hope it is familiar for you. This is the limit of a function, which is rather complicated, like f of x minus f of a over x minus a, but it's only the limit of a function, nothing else. Agree?
Yes, I agree.
Is
Agree.
it clear, Eric?
Yes, it's clear for me.
So you see, so now formally, I define my derivative like a limit as x goes to a, f of x minus f of a over x minus a, nothing else. So if you have, you see, then we say that my function is differentiable on some subset of R, capital R, if this function has a derivative for any point of this subset. You see, for example, if some function, we will discuss this, if some function is derivative for any point of the interval, of the closed interval 0, 1, so we will say that this function is differential at every point of this interval 0, 1. You see, so you can replace this set capital G by any interval of a real axis. Is it clear?
Yes, it's clear.
Good. Now, you see, formally, as for this slide, if I take, you see, if I take a function f of x, which is x, and I take any point a from the real axis, then you see it is very easy to find the limit. F of x minus f of a over x minus a, that is the limit. F of x is x, yes? So x minus a over x minus a will be the limit of 1, that is the derivative of this function f of x, which is x, is 1 for any point a of the real axis. Agree?
Yes, I agree. That makes sense.
Yes.
Agree? Valentina, agree?
Yeah, I agree.
Yes, I agree.
Onya, agree? Good.
Yes.
So you see, the second example is the my favorite function x squared. I like this function. Because I can give a lot of examples, a lot of applications, so on. So let's take f of x as x squared. Then you have in the numerator, you have x squared minus a squared by the definition, uniquely, by the definition. Then x squared minus a squared, I hope you know that it will be x minus a multiplied by x plus a. Then x minus a disappears. And you know that the limit of x plus a as x goes to a will be 2a. So this means that for any point a of the real axis, you will have that your derivative will be 2a. For any point. This means, in fact, if I take my function x squared, then its derivative will be 2x for any x of the real axis. Agree? Is it clear?
Yes, it's clear.
Yeah, it's clear.
Yes,
So-
it's clear for me.
So it's the beginning of our story. Now we will study something more interesting. Let's discuss the function which is given by the formula f of x equals absolute value of x. And can you imagine this function? Can you imagine this function, absolute value of x? Who knows?
Yes.
Yes. Yes, yes, no. Can
Yes.
you imagine? Can you say what's this? The absolute the graph of at least the graph of this function, absolute value of x.
It's one positive, one negative, like a B.
No.
It's two straight line. So
Yes. Yes.
if
But
the direction is in, if I have the plan that in, okay, is for always is in the sense of right hand, because always is
stop,
positive.
Valentina, stop. You see, it's the angle in some sense. Yes, two lines, two lines. And as for the value of this function at the point 0, what's this?
0.
0. So if x is positive, then f of x is x. Yes?
Yes.
Yes. If f if x is negative, then f of x is minus x. Okay?
Yes.
Okay. So the question is, so if you take, we see from the first example, if I take f of x equals x, I have no problems. I have no problems. The derivative exists. Okay? It's the same thing if I take f of x minus x. Okay? I will have my derivative. Instead of this result, as for minus x, you will have that your derivative will be minus 1. Agree?
Yes, I agree. It makes sense.
Good. So, as for this function, absolute value of x, the situation is not very good. Is not very good. Let's try to find our limits. You see, the limits exist. We will see this. But so the first limit as x goes to 0 plus, so on the right, you see, I have to write that it will be the limit of the absolute value of x over x, but absolute value of x is exactly x for positive numbers, for positive x. So it will be 1. But if I take my limit as x goes to 0 minus, so for negative values, I will have minus 1. Is it clear for you?
Yes, it's clear.
So, you see, due to the definition of the limit, you have the limit, the right hand limit and the left hand limit, which are in fact different. So the limit does not exist.
Okay, yeah, I get it. I get it.
Clear? Valentina, clear?
Yes, it's clear.
Vanya, clear?
Yes, it's clear.
So you see, in this case, in this example, you can see that for all x from the real axis, my function f, which is the absolute value of x, is differentiable, but it is not differentiable at the point 0. Only one point, but it's a fact. Agree?
Yes, I agree.
Agree.
I agree.
Good. So now it's an information for you. I don't know is it useful, but I think it will be useful. So if my function, without proof, evidently, if my function is differential at some point, then this function will be continuous at this point. So we can prove this due to definition of the continuity and the definition of the derivative of my function. So all the question to your lecture. Agree? But I want to underline this interesting point. Okay, so S4 the properties of my derivative. So you see, if I have two functions which are differentiable at some point of an open subset of my real axis, so f, g are differentiable, then the sum or the difference f plus g is also differentiable. And moreover, you see that the derivative, for the moment, I am speaking only about a fixed point of my real axis. So if I take the derivative of the sum of two functions at some point a, then it will be the derivative of the first function f at this point plus or minus, if you want, same thing, of the derivative of my function g at this point a. I think it was in your lectures. The second point of this theorem, if I take any constant, any real constant, and then my function, this constant c, capital C, times f is differentiable, and the derivative of this function c f is my constant multiplied by the derivative of my function at this point a. You know this, I hope. Onya,
Yes.
est-ce que tu connais ça? Really?
Oui.
Très bien. So, the third point, if I take a product of two differentiable functions, f and g, so the derivative of this function will be the derivative of the first function multiplied by the second one plus the first function multiplied by the derivative of the second function. Finally, the most complicated, if you want, formula for the derivation is the formula f over g prime at some point a. So you see, you have to know from your lectures, there is a formula for this quotient. So you see how to memorize this formula.
Excuse me, I have a question. That
Yeah.
formula has a name, right? Like a specific name.
Pardon? Pardon?
The formula has a specific name, right?
The formula, I don't hear well.
Hello, you can hear me?
Yes, I hear, but louder.
Yes,
If
the
you-
formula that you're giving us has a specific name, right?
The formula I give you,
It's a derivative of a quotient.
yes,
It's
yes,
the quotient rule, yeah.
yes, yes, evidently. Can you see the slide? Can you
Yes,
see
yes,
the
yes,
slide?
yes.
Yes, I can see the slide.
So you see how to memorize this formula. How to memorize this formula. I write here. Can you see what is I don't know dashed on the slide? Yes. Can you?
Yeah.
So you see, what do we have in the numerator? We have that I take the derivative of the numerator, that is f, and I multiply this by the denominator g, okay, minus the derivative of my denominator multiplied by my numerator and divided by my denominator to the point 2. So I repeat, it will be good because so the derivative of the numerator, okay, multiplied by the denominator minus the numerator multiplied by the derivative of the denominator, okay? And all this is divided by the denominator to the second power. I
Yeah.
agree.
Yes.
Yes, I'm
So
understanding.
it is only how to memorize this formula. So numerator prime, denominator minus numerator, denominator prime divided by denominator to the second power. Okay. So now you see here you have the table of derivatives. What is important? All these formulas are important. I think you can get another formulas, but these formulas are standard, and you have to know these formulas. You see, for example, you see the second point here. You have the derivative of the square root of x, but in fact, the formula number 2 is exactly the formula number 4 if you take alpha equals 1/2. Agree?
Yes,
Yeah.
yes, yeah.
Good. So we will not discuss all the formulas now, but maybe if you want for you what is important. Or, for example, points 8.9 for the trigonometric function, points 10, points 11. And then as for the inverse functions, I think today we will discuss how to get these formulas. But as for, you see, for you, Eric,
Yes.
so try, let's try, not now, let's try to find the points 8 and the point 9. Let's try to find. So you take, Valentina, also for you. Onya, also for you. So you take the definition of the derivative and you take your function sin x or cosine x and try to show that points 8 and 9 are good. You see, you understand the question.
Yes.
Yes.
So you take your pen, no, not now. You take your pen, you take the definition of the derivative and try to find, because it is not very difficult to find, but it is useful. Okay? Well, now, what is important? What is important? It is the next slide. The next slide, which is the chain rule. The chain rule. So, I do not read what I write here, but can you imagine a composite function? What is a composite function? What do you know about? How can you imagine this? Eric, what do you think?
A composite function.
So, for example, you see the best example, it's my favorite function, x squared. You have two functions. The first one is the function x. The second one is the function, if you want, x squared. So it is not very easy to understand, but so
It's like two functions that depends on each other, right?
yes,
Okay.
if you want. The second example, what I like, if you take one function like x squared and the second function sin x, so the composite function will, for example, will be sin of x squared.
Yeah. Okay, I understand. Yeah.
Clear?
Yeah, it's clear. It's
So-
like when you substitute a function into another function and you kind of.
Yes,
Okay,
exactly.
perfect.
Good explanation. I agree. So you see, this formula 1.1 gives us a rule which is known like chain rule, how to find the derivative of this complex or composite function. You see, for example, if I take, you see, I take a function h of x, which is 3x to the power 4 plus x plus 7, and all this to the power 15. You see, there is a very good and very simple method, maybe, I don't know, to find the derivative of this function h. For example, we expand the 15th power, and then we will have a polynomial. Agree?
Yeah, I agree.
It is possible, but as for the 15th power, it is not very easy to write all the coefficients and so on and so on. So we will use in this case our chain rule. So we have, for example, f of x is the function, is the polynomial 3x4 plus x plus 7. And then I can write that my function h, which is g of x, is in fact f to the power 15.
Yes, it's clear.
Yeah. So we use stupidly or directly, if you want, this chain rule theorem. So you see, where is the important point in this theorem? I will show you. Here, you see, you're right. G prime of f of a. Then it is multiplied by f prime of a. So we do not write exactly the argument. You see, in fact, in the first term, we take the derivative with respect the argument of the function g. For the moment, maybe I do not know which is the argument, but I have to take my derivative with respect to this argument. You see? So, the example, you see? I write that my g prime of f of a is 15. You know, okay, you do not know, but from the table of derivatives, you have to know. It will be 15 3x a4 plus x plus 7 to the power 14. And then, you see, the second term, we take the derivative exactly with respect the argument x. It is an important moment, so you have to think a little about this, and maybe you have some questions. Is it clear or not,
Clear.
this chain rule?
For now, it's clear for me.
Valentina, you see, for you will explain to your colleagues. You see, in fact, if I take my formula 1.1, you see, in some way, I do not read the details of this theorem, but your function g depends on something like y. You see,
Yeah.
y is f of x, okay?
Yes. Okay.
So if you take the first derivative, it will be the derivative with respect to y. And only the second derivative of my function f will be the derivative with respect to x. You see? Is it clear? Yeah?
Yes, for now it's clear.
Eric, is it clear?
Yeah, it's clear.
No. If you have some questions at the moment, nothing special, we will discuss, I will repeat, no problem. But it is important. You see,
I
if you are,
only want to know if it's necessary to change the variable x for the variable a, or it's the same.
maybe, you see, Valentina, maybe it's not a good, it's a good formulation of the theorem. Maybe I prefer dealing, I prefer to deal with the variables x, y, etc., so on. But you see, the main problem as for this chain rule is to explain that you have to find the derivative with respect to the argument of the function g. Maybe it is better to say that I have that my function g is depends on y and y is f of x. Maybe it's better. You see, so the first derivative is the derivative with respect to y, and the second one is the derivative with respect to x. Valentina, is it clear?
Yes, it's clear now.
Eric,
Yeah, for me it's clear too.
good. And for others,
So far, I'm good.
good?
Mhm.
Yeah.
It's clear.
Good?
Yeah, it's good. Yes.
Okay, so in this example, in this second example, it is just an application of this chain rule. I hope it is clear. Clear?
Yes, it's clear.
Good. Now, another information for you, which is, I don't know, you have to know this from the lectures. So the inverse functions. The inverse functions, and here we have some formula which is rather sophisticated because but maybe in as for the examples we can explain this, but you have to know from your lectures that the derivative of an inverse function, but attention please, Eric, attention. You see, f to the power minus 1 is the inverse to the function f. You see?
Yes, I see.
But attention please, you have the value of this function at the point y sub 0, which is f of x sub 0. And I can find this derivative by this formula 2.1, but it will be 1 over the derivative, but you see, at the point x0. So on the left-hand side, we have something depending on y0. On the right-hand side, we have something depending on x0. Attention, it is very important. I I do not ask, are you agree or not, because you have to know this from your lecture. But how to apply this? This is a good question. So first of all, you see, if you take the table of your derivatives, here you can find that the derivative of arcsine of x is something. So now we will try to prove this formula. We will try to prove this formula, okay? So the example. Let us show that the derivative of arcsine of, you see, sinus to the power -1. So the inverse function for the arcsinus of y. So first of all, if you, I hope you know the graph of the function sine. You know this.
Yes.
So you see, if I take a part of this graph, only a part of this graph, so a monotone part of this graph, I don't know, is it do you know this from your lectures? I take only a monotone part. So the part between minus pi over 2 and pi over 2. Can you imagine this? The part of this graph. So in this case, you will have that your function will be between -1 and 1. Okay? And only on this interval, we define our function arcsinus. Do you know this? It is not very easy, I understand. But do you know this?
Yes, this part is no.
Valentina, you know this?
Yes, about this part. The definant of the inverse, yes.
So the inverse function for sinus, it is not a very difficult problem for you, I hope. Okay? Then, you see, if I write that arcsinus of x is y, then knowing that the derivative of my function sinus is cosinus, in the corresponding, you see, in the corresponding interval, then what can we have? Arcsinus of y, you see, by this theorem, we have two different, in some way, two different points. I will show you once more. You see here, on the left-hand side, you have y, and on the right-hand side, you have x, okay? But usually we want to have we want to have our derivative in terms of the same variable. Okay? You understand?
Yes, I understand.
Eric, clear?
Yeah, it's clear.
So you see, first of all, I write that by this formula, by this theorem, the derivative of my arcsinus, but at the point y, you see, with y, which is like this, so the absolute value of y is less than 1, but it will be 1 over sinus prime of x. So 1 over cosinus of x. So our goal is to rewrite this inequality in terms of y. You see, to this end, you see, I write that cosinus of x is square root of 1 minus sinus square, but I know that sinus of x is y, you see, is y. So I write that, in fact, it will be 1 over square root of 1 minus y square. Is it clear?
Yeah, it's clear.
Yes, it's clear.
Clear. Agree? Then you see there is the question of sine in front of the square root. You will read this because as for cosine, it will be another root, but not for now. So another example in this way, in this topic, it will be arctan, arctangent of y, and it is a very useful formula for this derivative. You will use this formula a lot of time. So it is exactly the same situation. You see, I write formally by our theorem for the inverse function that the derivative of my function arctan, but at the point y, you see, I underline this once more, it will be 1 over the derivative of tangent of x, but at the point x. So let's take our table. You see, it will be 1 over cosinus square. Okay? I write this. It will be 1 over cosinus square. Then, evidently, 1 over cosinus will be cosinus square of x. Okay? For the moment, no problems, I hope. Eric?
No problems.
No problem. So you see. Now, cosinus square of x is in fact cosinus square divided by 1. Yes?
Yes.
Yes. So in my denominator, I write 1 as cosinus square of x plus sinus square of x. Agree?
Yeah, I agree.
Yes.
Agree.
Yes,
Very
sir.
good.
Agreed.
So So if we divide the numerator and denominator by cosinus square, then you see you will have in the numerator, you will have 1 evidently, and in the denominator you will have 1 plus tangent square of x. Agree?
Yes, I agree.
So you see tangent of x is y. So you will have that it will be 1 over 1 plus y squared. So the desired result. Clear?
Yes, it's clear.
Yes, it's clear.
Good. So now we pass to another topic, the higher order derivatives. The idea, only the idea, you can read the slide, there is no problems. So the idea, you have a function, you see, and you can obtain its derivative. For example, if you have sinus x, you can obtain that its derivative is cosinus x. The question is, maybe I can find the derivative of this derivative. In this case, I will obtain the second derivative of my initial function. You see, the second derivative. So the derivative of the derivative.
Professor, for what is useful the second derivative?
Oh, poor girl, you will see in your future course that it is very useful. So, for example, in order to study the behavior of the graph of the function, in order to plot the graph of the function, it is very useful. It is very useful. You see? So attention please, because the high order derivatives, this is not only for the course, but in order to understand the behavior of the function. We will see this, I hope we will see this in our future.
Okay, good.
Donc, so for now, no comments, because unfortunately I cannot give you all the applications of the second derivative and the higher order derivatives. You see, so for now you have to believe me that it is useful.
Okay, it's clear, Professor.
So, as for the derivatives, the next definition, the derivative of order n, we can define this like the second derivative starting from the first one. And the definition is here. Is it clear in general?
Yes, it's clear.
Valentina, is it clear?
Yes, it's clear.
Okay, so you see, for the moment, we have something like the derivatives of order n starting from the first one and then to n. Now, what can we do with these derivatives. First of all, which is very popular in our university, as for the exams and as for the written works, you see, here is the so-called Leibniz formula. This Leibniz formula is the nth derivative of a product of two functions which have the derivatives of order n. You see, the formula is 3.1. And the coefficient capital C and K is given here. So you see, usually as for the student, the favorite question is to ask, find the nth derivative of the product, and they give you the functions u and v in order to have this nth derivative. You see, so attention please. I don't know as for the program of this written exam, but you have to know this formula. Okay?
Okay.
So in some way, you see, Eric, in some way, if you close your eyes, and you imagine the binomial theorem, you can see this formula. In some way, it's just the same thing. I do not want to say the same thing, but something like, you see, if instead of your derivatives you take the powers, you will obtain your binomial theorem.
Yeah, I understand. Okay.
Valentina, clear?
Yes, it's clear. For me, it's clear.
Onya,
Yes, it's clear.
really? C'est bien?
Oui.
Comprends? D'accord. Okay. So, next slide. So, for example, you see why we have to use this Leibniz formula. So here we have an example. So our function y is a product, but very simple, of two polynomials. 2x plus 1 to the power 3 and x minus 1. And we want to find all the derivatives of nth order from n equals 1 to n equals 5. So in this case, you see, in order to show you where is the advantage of this Leibniz formula. So in this example, we will find all the derivatives directly from the definition. So first of all, from our definition, we can convert our function y to a polynomial. You see, we will have something like this. So no arithmetic problems. I hope you can do this yourself. So you will have a polynomial, something like this, no problem. Then, if I take the first derivative, due to our I will show you once more. Once more, you see you have x alpha, x to the power alpha. The derivative of x to the power alpha is alpha multiplied by x to the power alpha minus 1. So, for example, if I have x to the power 3, so the derivative of x cubed is 3x to the power 2. Agree?
Yes, I agree.
So then, if I take the derivative of my polynomial, I will have something like this. Then the second derivative, it will be the derivative of the derivative. Yes. So I have to find the derivative of this polynomial. I will have something. I don't know what. So the third derivative, it will be the derivative of the second derivative. So it will be something like this. Finally, the fourth derivative, it will be a constant. Agree?
Yeah, I agree.
Clear for all? No problem.
Yes, it's
Mhm.
clear.
Good. So the fifth derivative will be the derivative, attention, will be the derivative of a constant, in this case, 192. So the fifth derivative will be 0. So, but in this case, you see, we use only the fact that we can convert our function to something like a polynomial and then find all the derivatives. So we do not use this Leibniz formula. We do not use. Another situation with the nth order derivative is the derivative of the logarithmic function. Y equals log of x. I think you know this function.
Yeah, we know it.
You know. Very good. So, as for the first derivative, you can check using the table of the derivatives that the derivative of my function y is 1 over x. So now I can use the table of derivatives in order to find second derivative as the derivative of the first one. And using this table, you see, I will repeat you because maybe it was not clear. You see, here I write x to the power alpha. Alpha can be positive or negative. No problem. Understand? Is it clear?
Yeah, it's clear.
Yes, it's clear.
Good. Thank you. So you see, in this case, you have the derivative of x to the power minus 1. So in this case, alpha is minus 1. Then you can find the derivative of this function. In the same way, you can find the third derivative of this function, the fourth one, now, even the fifth one. So why we do this? In order to find the hypothesis about the nth derivative of my function y. And this hypothesis is given by the formula 3.2. You can check, but you see that at least for the first, second, third, fifth derivative, it's good. But we want to find our derivative for any n, for any natural n. So in this case, I recall you that we can use the method of mathematical induction. So we check this formula for n equals 1, and then what do we have? I want to calculate the n plus 1, the derivative of the order n plus 1. You see? So I have to derivate my formula 3.2. I do this using my table of derivatives. And then I will find that the derivative of order n plus 1 is given like this. So this is a justification of my formula 3.2. Is it clear?
Yeah, it's clear for me.
The girls, is it clear? Valentina, is it clear? Or maybe you have questions?
The proof of the 3.2 is the final, yes? The final result of first grade.
Yes. You see, we claim in our class, we claim that the nth derivative, the nth order derivative of y is given by 3.2, because I can imagine this from the first, second, third, fourth, fifth derivative. Okay? But we have to justify mathematically in a rigorous way this formula. So we use the method of mathematical induction.
Yes, okay, it's good.
Good. So what do we have? We have. So what I propose to you, because we have not, so we have 8 slides. I propose you a little break, and then we will finish in 15 minutes. Okay?
Okay, it's good.
Okay, sounds good.
Okay.
So see you.